This video is sponsored by Boot.dev. In the last video, we finished the analysis part of the compiler. At this point, the program is syntactically correct, semantically valid, and its types all check out. And now that we have the program in this high-level form, it's the perfect opportunity to start optimizing it, before we eventually bake the whole thing down into ones and zeros. The first thing you might think of is the big optimizer, the part that makes your code actually run fast. That does exist, but it usually lives later on, operating on an intermediate representation that we'll look at in the next video. Before we even get there, there's already a surprising amount of work happening on the AST itself. Some of it is plain cleanup, some of it is about the language desugaring into a smaller core, and some of it already gives a speed boost to the resulting program. Hi and welcome to Premature Abstraction. This is the 5th video in a series where you learn all about compilers, one of the oldest and still most important topics in computer science. The goal is that by the end, you'll even be able to write one yourself, so please subscribe if you don't want to miss that. In this video, we'll go through transformations and optimizations on the AST. Let's start with cosmetics. The parser produces a tree that directly represents the source code, which means it often carries pieces that don't actually mean anything. Redundant parentheses, for example, can be dropped, because the tree already encodes the grouping. Same for a redundant cast from int to int, or a unary plus in front of a number. Python, for example, even lets you write 4 minus signs in a row in front of a 5, which is just 5, and the compiler can collapse that immediately. A slightly more interesting case is when the language has multiple ways to write the same thing. Take a chain comparison like a smaller than b smaller than c, and the equivalent a smaller than b and b smaller than c. They parse into completely different trees. In some languages, the compiler can normalize one into the other, so later stages only have to deal with one shape. Nothing is getting faster here, we're just making the tree more uniform. But already this tiny transformation is a good first hint at how easily optimizations can go wrong. In this example, the two forms aren't actually equivalent. The first one evaluates b only once, while the other one evaluates it twice. So if b is any expression with a side effect, the two programs behave differently. This idea of different syntax, same meaning leads into one of the most common kinds of AST transformation, desugaring. Most programming languages have a smaller core that the compiler actually cares about, and a whole lot of syntactic sugar layered on top of it. The parser understands the sugar, but later stages don't have to, because the compiler rewrites it into the core before anything else looks at the tree. A classic example is the for loop. In most languages, a for loop can be expressed as a while loop, so the compiler just rewrites one into the other, and from that point on only whiles exist. Or think about list comprehensions, which could get transformed into loops in exactly the same way. In Python this is not actually the case though. List comprehensions have their own code object. Destructuring assignments like const x, y equals object turn into this. Even something like a plus b might get rewritten, because if the language allows operator overloading, the plus is really a call to some underlying method, and once that rewrite happens, the rest of the compiler just sees a function call. Some desugarings are much bigger than that. Async and await in languages like Rust, C# or Kotlin get rewritten into state machines. The compiler literally generates a new data type that tracks where the function was suspended. And in JavaScript, the class syntax is just sugar for functions and prototypes. Alright, but how does the compiler actually decide which transformations are allowed? This brings us to the single most important principle on this whole topic, something called the as-if rule. The idea is simple. The compiler can do whatever it wants to your code, as long as the observable behavior of the program stays the same. It can reorder things, delete things, inline things, pre-compute things, as long as a user running the program can't tell the difference. That's a much looser constraint than don't change the code. And it's exactly what makes optimization possible in the first place. The tricky part is figuring out what observable actually means. It's not just the final output. It also includes side effects like writes to memory, I/O, exceptions, or thread synchronization. So before the compiler can safely rewrite an expression, it usually has to prove that the expression is pure, that it has none of those side effects. You'll see later that almost every caveat in this video boils down to the same thing. The compiler would love to rewrite something, but it can't prove the expression is pure for every input. If you're watching my channel, you're definitely interested in learning about computer science topics. This is why I'm excited about this video sponsor, Boot.dev. Especially in the age of AI, it's important to get the fundamentals of software development right, and Boot.dev is the perfect platform for that. On Boot.dev, you're not just watching someone explain things, but you're doing the actual coding yourself, either in the browser or locally from your terminal, using their CLI. They lean heavily into gamification with things like XP, levels and leaderboards, which was proven time and time again to help you keep motivated, even throughout the hard parts. They even have courses about memory management in C and Golang, which is a great fit if you're planning on building a compiler yourself. There's a whole curriculum of backend development courses beyond that, covering everything from SQL and Docker to cryptography and Kubernetes. All content is free to read and watch. But if you want to get the full interactive experience with hands-on coding and progress tracking, use my code abstraction for 25% off your first year. They also have a 30-day refund policy with no questions asked, so there is literally no excuse not to try it. Now, we can finally talk about an actual optimization. The simplest one is called constant folding. If the compiler sees an expression whose result it already knows, it just replaces the expression with the result. So 3 plus 5 becomes 8. A plus B plus C becomes ABC, and a function that just returns 5 plus 3 can be folded at the definition. This sounds trivial, but actually it's full of pitfalls. Take 0 plus foo. That is fine, it's equivalent to foo. But 0 times foo? You'd think that's just 0, except foo might have a side effect or throw an exception, and then just 0 behaves very differently from the original program. And even with the other example we need to be careful, because 0 plus can trigger an implicit typecast depending on the language specification. Same thing with a minus a. In a single-threaded world, that's obviously 0. But if a is shared between threads, deleting that read might change what another thread observes. And we need to respect the language's memory model, even though in 99% of cases this would probably be a race condition bug. C actually has a volatile keyword specifically to tell the compiler that this must not be folded away. Floating point makes this even worse. A plus B in brackets plus C and A plus B plus C in brackets may produce different results in IEEE 754, so the compiler is usually not allowed to reassociate floats. And not a number propagates in ways that break a lot of algebraic identities you might expect to hold. This is why GCC and Clang have a flag called fFastMath, which basically says, pretend floats are real numbers, I accept the consequences. One more issue is that the compiler might not even be able to evaluate every constant expression by itself. If you compile a Python program with a compiler written in C, the compiler probably can't fold arbitrarily large Python integers, because its own integers are bounded. So the compiler has to be careful about folding anything it can't actually evaluate itself. Constant folding has a close friend called constant propagation. If a variable is always the same value, the compiler can substitute that value wherever the variable is used. So the x can be replaced here, which folding then turns into y equals 8. This is also why immutability is so useful for compilers, and modern languages tend to shift the default for variables to be immutable. The more the compiler can prove a value never changes, the more it can substitute and fold. There is a sibling of this called copy propagation, which works for non-constant variables. If you write x equals y and z equals x plus 1, the compiler can rewrite it into z equals y plus 1. X is now unused, which sets up the next optimization. Often there are statements or whole functions in a program that will never be executed, so-called dead code. These can be removed in a process called dead code elimination. The clearest cases are branches that can't be taken. If false means we can drop the whole block. If true means we can keep the body but drop the condition and the else block. Or unreachable arms in the pattern match. Or comparisons that are already decidable at compile time because of the types. Variables that are written but never read can be removed, and functions that are never called can be dropped entirely. There's a whole family of control flow cleanup that happens around the same time. Nested ifs with the same condition get flattened. Empty branches get deleted. Boolean short-circuiting gets applied wherever it's safe, so true and a condition becomes just a condition. This is also the reason many languages made their Boolean operators short-circuiting by default, because full evaluation is rarely what you actually want. Before we get into bigger transformations, I want to take a quick moment to thank everyone supporting the channel on Patreon. You're the reason this series keeps going, and I really appreciate it. If you'd like to join them, the link is in the description. Now let's talk about function calls, because these are one of the places where the compiler can save a surprising amount of time. A function call itself is not free. We will get into the details of how this works in later stages of the compiler, but arguments have to be passed, a stack frame has to be set up, Registers have to be saved and restored, and the optimizer usually can't see through the call. It doesn't know what the callee does, so it has to assume the worst. Maybe the function modifies some shared state, maybe it throws an exception, maybe it never returns. Any value the compiler would have cached in a register might no longer be valid afterwards, so it often has to redo work it would otherwise have reused. Inlining fixes all of that at once. Instead of doing a function call, the compiler pastes the body of the callee directly into the caller, and suddenly a whole new round of folding propagation and dead code elimination becomes possible, because constants can now flow from the caller into what used to be the callee. Some languages let the programmer ask for this explicitly. Kotlin and C have an inline keyword, Rust has the inline attribute. But inlining is not free either. Inlining a large function everywhere blows up the binary and hurts the instruction cache. Recursive functions can only be inlined to a bounded depth, or it's just not possible at all, for example when function pointers are involved. So compilers use heuristics. If a function is small and called in a hot loop, it's a good candidate for inlining. Inlining is also a big reason modern programmers don't have to trade off readability against performance. You can happily split your code into lots of small, well-named helper functions for clarity, and trust that the compiler will fold the ones that matter into the caller anyway. A close relative of inlining is devirtualization. In an object-oriented language, a method call is normally indirect. The compiler doesn't know which implementation will actually run. That's decided at runtime via a vtable. But sometimes the compiler can prove the answer ahead of time. If the method is final or an interface has only a single implementer, the indirect call can be turned into a direct one. And once it's direct, it's a candidate for inlining again, which is usually the whole point. Then there is tail call optimization. If a function's last action is calling another function, the current stack frame can be reused. The scheme programming language specification actually requires a compiler to do this, and functional languages like OCaml or Haskell lean on it heavily, because they use recursion where imperative languages would use loops. Interestingly, the designers of Python ruled out adding tail call optimization once and for all, not only because clean stack traces are more important than cheap recursion to them. And finally, there's a quieter form of call optimization, where the compiler recognizes patterns it knows how to do better. It spots calls to standard library functions like memcopy, string length, or square root, and even handwritten loops that do the same thing, and then rewrites them into special nodes the backend understands natively. That often means that a manually written byte copy comes out a few stages later as a single SIMD instruction. Pushing the idea of folding further, we arrive at a whole category of transformations about running code at compile time. Constant folding is just the smallest version of this, but modern languages take it much further. Rust has const function, which lets you mark a function as runnable at compile time, so the compiler will evaluate it during compilation when it's called in a const context. C++ has const expr for the same purpose, with const eval to force evaluation. Zig takes this further with comptime, which lets you run essentially the whole language at compile time and treat types as first-class values that functions can compute and return. A related but different idea is macros. Macros run at compile time, but instead of producing values, they produce code. Actual AST nodes that get spliced into the program. The C preprocessor is the best known one, but it's a bit of an outlier because it operates on raw text, not on the AST. Lisp's macros are arguably the cleanest design, because code and data share the same representation, so macros literally manipulate lists. By the way, let me know if I should make a video about this, it's really fascinating stuff. Rust has two flavors: declarative macro rules, which work on token patterns, and procedural macros, which run arbitrary Rust code at compile time to rewrite pieces of the program. By now you've probably noticed that these transformations feed on each other. Constant propagation makes folding possible, which makes dead branches visible, which makes more variables unused, which makes more propagation possible, and so on. So instead of running each pass once, compilers run a whole set in a loop until nothing changes anymore, a so-called fixed point iteration. And the order of passes matters a lot. Compiler engineers spend a lot of effort on what's called phase ordering. This is also where these compiler flags you've probably seen fit in. O0 means don't optimize anything. Keep the compilation fast, keep the code one-to-one with the source. O1, O2 and O3 turn on progressively more passes, at the cost of longer compile times and potentially larger binaries. OS and OZ optimize for binary size instead of speed, which matters a lot for embedded systems or WebAssembly. There is even OG, which means optimize as much as possible without ruining the debug experience. And that's the catch, because optimized code is quite painful to debug if half of the actual written code is optimized away. Inlining and reordering mean line numbers in a stack trace don't match anything recognizable anymore. This is why release builds and debug builds exist, and why production crash reports come with huge symbol files that try to undo the damage after the fact. There is also one last category I want to mention: destructive transformations, ones that actually change what the program does. Normally those are forbidden by the as-if rule, but when the language spec declares a behavior to be undefined, the compiler is suddenly allowed to assume it never happens and optimize it accordingly. C and C++ are famous for this. Signed integer overflow is undefined, so the compiler assumes x plus 1 is always greater than x. Null pointer dereferences are undefined, so code that reaches 1 can simply be treated as unreachable. This is a rich source of security bugs, and it worked at 0.0 but not at 0.2 horror stories. And that's the AST optimization stage. Some of it is plain cleanup, some of it is helping the rest of the compiler with a smaller core language, and some of it is speeding things up. And taken together, all of this is really what lets you focus on writing clear, well-architected code, without having to hand optimize everything for performance. But this is really only the first pass of optimization. The AST is actually not a great data structure for serious analysis, because it follows the shape of the source code, not the shape of the program's control and data flow. And up to this point, we also don't know the target architecture, so a whole class of optimizations isn't even on the table yet. In the next video, we'll introduce the intermediate representation, a different form that lets the compiler ask much more precise questions about what the program actually does, and optimize a lot more aggressively. This has been Premature Abstraction. Thank you for watching.